In your prep class, you did learn a little bit about empirical and molecular formulas. We're going to review some of the stuff that you learned then, and then we're going to take it up a notch, and we're going to look at, other than just percent composition, some other things we can do for empirical molecular formulas. At the end of this section, I have 2 challenge problems. The challenge problems, I will give you a couple of solving hints, but then the challenge will be for you to solve them on your own. There will be a separate assignment submission on Canvas for the 2 challenge problems that I want you to try on your own. They might be a little bit of a struggle. They might be a little hard, but that's the point. You have time at home. I want you to struggle with them. Don't try to look them up or anything. The goal is not just the right answer. The goal is the process and the struggle and the trying to figure out the answer. All right, because that's a lot of what science is. You've got this puzzle. How do we solve the puzzle? All right, so let's get into it. So remember our empirical formula, that's just the smallest whole number ratio of each component. We can look at this from percent composition, from combustion analysis, which we'll go over, and then there's all sorts of other little things where we can, if we don't have a cut and dry method, we can do some other things to figure it out. And then the molecular formula is the actual formula. So, the empirical formula might be a 1-to-1 ratio. Cool. So we'd have 1 of this and 1 of that. But maybe the molecular formula is like 4 of this and 4 of that. Okay, so it'll be a whole number multiple of that empirical formula. Okay. When we talk about mass, remember sometimes we say atomic mass or molar mass, molecular mass, molar formula, but I'll get used interchangeably. Okay, we can do this in AMU or grams per mole. And so grams per mole is the one that we use most frequently, right? Because we're saying we have this many grams of this substance per mole. All right. So we're going to start off with just kind of getting back in the method of dimensional analysis and just taking a look at puzzling something out. So here we have a problem. All right. We've got some nitrogen fixation occurring. We've got a reaction with a molybdenum containing enzyme named nitrogenase. Now, enzymes are really large. Enzymes are what we call macromolecules because they're so big. In this particular enzyme, we have 2 molybdenum atoms per molecule, and we have 0.0872% molybdenum by mass. We want to know what the molar mass of this enzyme is, and I'm going to tell you right now, it's huge because enzymes, macromolecules, very large. If you've taken biology classes, you might have encountered these. If you are studying biology and you end up taking biochem and stuff, you'll definitely encounter more enzymes. Okay, now there's a couple of things that will help us solve this problem. All right, so we have some information. Okay, we have this 0.0872% molybdenum by mass, which means I have 0.0872 grams of molybdenum for every 100 grams of enzyme. Okay, so that's going to be an important thing to understand. We also have 2 atoms of molybdenum for every 1 molecule. That's our enzyme. Okay, or we can also look at it from the terms of 2 moles for every 1 mole of our enzyme. Okay, right? Because if I have 1 mole of water, I have 1 mole of oxygen atoms. If I have 1 single water molecule, I have 1 single oxygen atom. Okay, so these 2 things are going to be very important to keep in mind, what we've been given in the problem. Now we want to know the molar mass, okay? And so what did we just say about molar mass? Well, molar mass is going to be the grams of our compound over moles of compound. Okay, so we need to take that given information and figure this out. Now, from our information, we get some stuff about grams of molybdenum, okay? But I need to get to something else because I have a relationship between moles of molybdenum and moles of my compound. I also have some information about grams of molybdenum per grams of my compound. So I need to somehow get to moles of compound and all of that too. So is there a place we go to get some information about going between grams and moles? Our periodic table. If we look at our periodic table, we find out that for molybdenum, it is 95.96 grams per mole. So let's take a look. What if we do this? What if I have 95.96 grams of molybdenum for every 1 mole of molybdenum? Okay, so far so good. Well, we need to get to a point where I have moles of compound. So let's get rid of moles of molybdenum. From what we were given, we have 2 moles of molybdenum for every 1 mole of our enzyme. Oh, okay. Is that going to cancel out moles of molybdenum on the bottom? It is. Okay, now let's figure out that grams of molybdenum. We need to go from grams of molybdenum to grams of compound. Oh, but that other piece of information we were given. I don't have to write it grams of molybdenum over grams of compound. I can flip-flop it. I can say I have 100 grams of compound. And in this case, my compound is my enzyme. For every 0.0872 grams of molybdenum. Okay, let's make sure we did this correct. Grams of molybdenum cancel out. Moles of molybdenum cancel out. So let's take a look. I need grams of my enzyme over moles of my enzyme. So here I have grams of enzyme over moles of enzyme. So did we do okay? If we do the math on this, are we going to get grams per mole of our enzyme? Yeah. Okay, so when we plug this in, we're going to get 220,092 grams of enzyme over every mole. Okay, that's huge. And we don't have that many significant figures either. We have a percent composition by mass that has 3 sig figs, so let's round. 2.20 times 10 to the 5th grams per mole. See, I told you it was huge. All right, so there's one way we can use percent data. But what we do need to understand, though, is how to do, what on earth is that percent by mass? So when we look at something, we can get a percent composition. So let's say I have this chlorofluorocarbono compound, okay? All right, I want to know the mass percent of chlorine. So the mass percent is the mass of the part over the mass of the whole. So in this case, the mass of the part is chlorine, and the whole is my chlorofluorocarbon. Okay, so my compound formula was CCl2F2, so mass of part over mass of whole. So I'm going to take 2 moles of chlorine times 35.45 grams of chlorine in every 1 mole of chlorine. Okay, there's the mass of my part over the mass of my whole, which is going to be 12.01 for carbon, 2 times 35.45 for chlorine, and 2 times 19 for fluorine. All right, so when we do all of this, we get 2 times 35.45 on the top over 120.91 on the bottom times 100, and we get 58.64% chlorine. Now, when I look at the formula, I have 5 atoms in my formula. Only 2 of those are chlorine. But I end up with 58.64% chlorine. Why is that? Because it's percent by mass. And if I look at this, the chlorine has a larger mass than the carbon or the fluorine. So it stands to reason that only two chlorines, even though the two chlorines make up less than 50% of the atoms in the compound, they do make over 50% of the mass because they have so much more mass to them. Okay? All right. So let's take a look at percent composition and figure out an empirical formula for this. Now, before we get going, I want to review something. Remember, okay, the empirical formula, it's been abbreviated as EF, must be a whole number multiple. Must be a whole number, okay? The empirical formula must be a whole number, all right? So sometimes we get the nice whole number, but what happens if we get certain decimals? Now, some decimals we can't do anything with. Like if I get, if I do everything and I end up with like 0.83, okay, I made a mistake somewhere. But let's say I'm doing this and, I'm looking at my carbon and my hydrogen and I get like carbon 2.25. That 0.25 we can do something with. So there's 4 decimals to look out for that we can do something with, okay? If after we do our division, if after we look at, carbon, hydrogen, divide by the lowest, we still get a decimal, okay? So if decimal still exists after the division for the ratio, okay, 0.5, 0.25, 0.33, or 0.66, okay? These are the 4 to look out for. What you do is you multiply the entire empirical formula, okay? Even the components that don't have a decimal. Multiply the entire empirical formula, okay, by, so if it's 0.5, you multiply the entire empirical formula by 2. If it's 0.25, you multiply the entire empirical formula by 4. And if you see 0.33 or 0.66, you multiply the entire empirical formula by 3, okay? So that way we get back to our whole number. All right, so again, that's after we do the division for the ratio of the 2 components to each other. If you still see some sort of a decimal, if you look for these 4, this is what you multiply the entire empirical formula by. Hopefully that's review. Your previous class should have gone over that. Fingers crossed, because it is a normal thing that we cover in that class. All right, so let's take a look at this one. We've got this polystyrene, 92.26% carbon, 7.74% hydrogen. What is our empirical formula? Well, remember, we make this assumption. If I have 92.26% carbon, I have 92.26 grams of carbon. Because what we're doing is we're saying, well, let's say I have 100 grams of my compound. Well, if this is out of 100, then 92.26% becomes 92.26 grams. All right, so that's what's easy about percent composition, is we're just assuming that we have 100% of the compound, 100 grams, boom, easy. Okay, so I'm going to take my 92.26 grams of carbon. I have 1 mole of carbon and 12.01 grams of carbon. I'm going to get 7.68 moles of carbon, okay? I have 7.74 grams of hydrogen. I have 1 mole of hydrogen for every 1.008 grams of hydrogen, and I get 7.67 moles of hydrogen. So carbon, 7.68, hydrogen, 7.67, okay? So here's where we do the division. Now, if after this step is where we still have one of those decimals, then we have to multiply the whole empirical formula. This is an easy one though, because 7.68, 7.67, they're basically the same number. They're all 5.01. This one's easy. All right, so divided by 7.67, divided by 7.67. Oh, look, our empirical formula is CH. Okay? All right, here is another one for you to look at. Also, just carbon and hydrogen. I want you to try it. I'm not going to solve the whole thing, though. Pause. Try it. Okay? I forgot to write the answer down on the last one. The last one you should have gotten CH4. Okay? So, do it yourself, but the answer should have been CH4. All right, now we don't just have to have carbon and hydrogen. Here I've got carbon, oxygen, and fluorine. Okay, but now I want the empirical and the molecular formula. In order to get the molecular formula, we need to know the molar mass of the compound. You cannot figure out the molecular formula without that molar mass. Okay? All right, let's try this. Okay, so I had my percent composition. Now we're going to get our mole. So I have 14.6% carbon, so 14.6 grams of carbon, 1 mole, 12.01 grams, 1.2157. Okay, 39. Alrighty, and then we have 49.3% fluorine. Okay, so we're gonna get carbon, oxygen, and fluorine. Okay, divide by the lowest. We're going to get CO2F2. Okay, so there is our empirical formula. Now, we want to know the molecular formula. In order to figure out the whole number to multiply by to find out the molecular formula, we need to do the molar mass of our molecular formula divided by the molar mass of our empirical formula. Okay, so I can figure out the molar mass of my empirical formula is 82 grams per mole. This is going to be easy. I get 82 grams per mole divided by 82 grams per mole. I get 1. So my whole number ratio that I multiply by is 1. So my molecular formula is CO2F2. Okay. All right, now let's take a look at what you may not have done in 120. Let's look at combustion analysis. So in combustion analysis, we take something and we burn it in oxygen. Usually combustion analysis is done with some sort of carbon and hydrogen containing compound. Okay, so I burn my stuff. All right, now what happens is all of the carbon is converted into carbon dioxide. All of the water in the original compound is converted into water. So I get hydrogen into water, carbon into carbon dioxide. I get these absorbers, and on these absorbers, they absorb the carbon dioxide or the water, and then I can weigh things out to figure out how much carbon dioxide I have and how much water I have. Anything else just goes out, doesn't get absorbed. And if let's say I have something that's carbon, hydrogen, and one other element. Well, if I know I have a whole, if I know how much carbon and I know how much hydrogen, I can figure out the other element by subtraction. Okay? All right, so here's another picture of it. There's the furnace, so absorption of the water. So again, right here, what happens is all hydrogen gets converted to water. So all hydrogen in okay, and then all alrighty. So that's what we're going to look at when we try to solve this problem. So I've got menthol. All right. It is carbon, hydrogen, and oxygen. All right. My sample of menthol is combusted. I produce some carbon dioxide. I produce some water. And so we need to calculate what our empirical formula is based on all of this stuff. Okay, so let's figure this out. So I need to know my carbon, my hydrogen, and my oxygen. Okay, so again, all my carbon converts to carbon dioxide. So if I know how much carbon dioxide I formed, I can figure out how much carbon there was. Okay, so 1. Okay, to determine moles of carbon, all carbon converts to carbon dioxide. Okay, so I have 0.2829 grams of carbon dioxide. Okay. All right, I have 1 mole of carbon dioxide. In every 44.01 grams. Okay, and I have 1 mole of carbon in every 1 mole of carbon dioxide. And so what I end up with is 0.006428 moles of carbon. Okay, and then to determine moles of hydrogen, all hydrogen converts to water. Okay, so for my problem, I have 0.1159 grams of water. I have 1 mole of water and every 18.016 grams of water. Okay, and then here's the real important one. This is where I see a lot of students make mistakes because the carbon dioxide is 1-to-1 with the carbon and the carbon dioxide. Well, I have 2 moles of hydrogen per every 1 mole of water. So it's 2 moles of hydrogen for every 1 mole of water. Okay, and so I'm going to get 0.012866 moles of hydrogen. Okay. Now, what I need is, for oxygen, I need grams of original compound, grams of carbon, and grams of hydrogen. Okay? So 3. Okay, I need grams of original compound, grams of carbon, grams of hydrogen. Okay, so far so good. There's a lot of steps to this, but it's very systematic. Okay, because if you think about it, we're burning it in oxygen, right? So there's excess oxygen. Carbon dioxide has oxygen. Water has oxygen. So I can't use either of those to figure out my oxygen. I have to do this grams of original compound, the grams of hydrogen, and the grams of carbon. Okay, so from above, I had 0.006428 grams of carbon, or not grams, moles. Try to determine grams. 12.01 grams in 1 mole. Okay, and so I'm going to get 0.0772. Okay, then for hydrogen, I had 0.012866. So for grams of hydrogen, it's 0.01297. Okay, so now I have my grams of those, so I can figure out grams of oxygen. So I had 0.1005 grams of my compound minus 0.0772 grams of carbon minus 0.01297 grams of hydrogen, which gives me 0.010331 grams of oxygen. To do an empirical formula though, I need moles, so now we got to convert this to moles. So 0.010331 grams of oxygen times 1 mole in 16. All right, I'm going to get 0.000646. All right, not a whole lot of oxygen. Okay, but now I have all of my moles. What I need is, I need the moles of carbon, I need the moles of hydrogen, and I need the moles of oxygen. Okay, because again, to do empirical formula, we need moles. All right, so I'm going to take all of those. So I have carbon, 0.006428, hydrogen, 0.012866, and oxygen, 0.000646. Okay, well obviously oxygen is the smallest because it has 3 zeros in front of it, so we're going to divide by that one. Okay, so when I do all of that, I end up with C10, H20, O. Okay, so that is how we do combustion analysis. Now, you're not going to learn it unless you do it on your own. So here is another one, phenol. Okay, also known as carbolic acid. We've got 5.23 grams of phenol. We get some carbon dioxide, we get some water, and we have carbon, hydrogen, and oxygen. We want to know the empirical formula of phenol. Okay, we get a molar mass of 94 grams per mole, so we want to know what the molecular formula is. So this one, I'm not going to do all the steps. I'm just going to give you a couple hints, final answers, because I really want you to solve this one on your own. You're not going to learn it unless you solve it on your own. If you just copy what I do, you're going to think you know it, and then you're going to struggle. Okay? All right, so remember carbon, going to get from the carbon dioxide, hydrogen from the water, and then oxygen from grams of compound grams of carbon, grams of hydrogen. Okay? So that's where all of those come from. All right, your empirical formula is going to be C6H6O. Okay? Now to do the molecular formula, remember you're taking the molar mass of one divided by the molar mass of the other. Okay? So you're going to take the molar mass of your molecular formula, and you're going to divide that by your empirical formula. If you touch the wrong thing, it like randomly erases what I'm doing. I think I do need a glove on my hand. Which is weird because this program that I bought to do this is built as a way to, draw on your iPad and have it mirrored on your screen. So I'll have to look into that. But anyway, when you do this, you actually get the same molar mass for both. So your molecular formula is going to be C6H6O. All right. So again, I wanted you to try those on your own, or try that last one on your own. Those are the final answers. I've given you the hint on the steps, but the work I want you to do. Okay, now the last two problems I have are challenge problems. Okay, my head cuts part of this off, but that's okay because you'll want to download the slides to try these. I'm just going to give you some hints about how to do it. This is for you to try. Now, they're challenge problems. If you don't want to do them, okay, you don't want to do them. The submission that will be up on Canvas will be an extra credit submission, and it'll be extra credit for your notes, okay? Because this is part of your note taking. So if you solve the two challenge problems, I'll give you a few extra points toward your note taking. Now, I do expect to see in your notes all the rest of the example problems. Remember, no example problems equals a 0 for your notes because that tells me you're not actually engaging with the course material. But these are challenge problems. So these are a little bit harder, but they're a good puzzle. All right, so for this problem, here are my hints to you. Okay, I'm going to give you a set of 4 steps. Okay, step 1 in solving this problem is calculate the percent composition for each element. Okay, because it tells you like, oh, all the calcium was made into calcium carbonate. Well, if you know something about calcium and you know something about calcium carbonate, you can figure out how much calcium was there and then figure out the percent calcium in that. And that tells you your percent calcium because you know the original compound. Okay, all right. Then you've got some stuff with sulfur and some barium sulfate, you know, some nitrogen and some ammonia, so you can get percent composition data there. And then carbon, well, I don't give you anything about carbon, but if you have 4 things, all 4 should add up to 100%. So if you know the percent calcium, if you know the percent sulfur, and you know the percent nitrogen, you should be able to get the percent carbon. Okay. So once you have those, once you have percent composition data, it should be fairly straightforward because once you're there, you can calculate moles of each component. Okay, then you can calculate the empirical formula. Okay, and I will tell you the final answer though. Okay, and then 4, calculate molecular formula. Okay, so your very final answer you should get is CaC2N2S2, which, oh, I have 2 carbon, 2 nitrogen, and 2 S. Now, what if I rearrange the orders of this? What if I rewrite it like this? SCN2. Okay, calcium thiocyanate. So your final compound is calcium thiocyanate. Okay, so there's your hint on that one. Okay. All right, now this one again, crazy problem, but you can do it. I have faith in you. Another challenge. So again, for the extra credit, both challenge problems. I'm going to give you a hint on this one too. Okay. So I'm going to give you a little bit of an interesting formula because it talks about when things are precipitated out. So I'm going to give you a hint here. Okay, so, okay. So notice X and X. Okay. All right. This precipitates out. This isn't an aqueous solution. This is a gas. Okay, again, note the Y and the Y. All right, and then we precipitate out the chloride with some silver nitrate because silver nitrate would be in solution to silver ions and nitrate ions. And if you put silver ions and chloride ions together, we precipitate out silver chloride. Okay, and we have some masses for these. So this was 0.643 grams. This is 0.222 grams, and we ended up with 0.996 grams of our silver chloride. Okay, and so for your moles of CH3, so you can get that formula there, you'll look at the methane. Remember X and X. For your chloride, you'll look at that silver chloride, Y and Y. And then for your aluminum, you can look at how much methyl ion, the CH3, or not ion, but methyl group, CH3, how much chloride ion, and then the grams of the original compound. Because, hey, if I have a grams of this crazy compound here, and I know how much CH3, and I know how much chloride, oh, I can subtract and figure out that aluminum. Okay? And then you can go from there. All right, so there's your hint on that one. Good luck. Try them. Please do them. Don't just pull them off because they're extra credit. Stretch your brain. Learning, it's a struggle, but it's a productive struggle. Sometimes it's really hard and you're like, oh my gosh, I can't do this. I can't do this. Do it. I mean, my kid does this all the time. I will be busy doing something and my kid will be like, mommy, help me, help me. I'll say, okay, just a minute. Give me a minute. 2 seconds later, oh, I got it. Okay, so resist that help me without trying it first, right? Because that's my kid's problem is the moment she encounters something that she's not sure if she can do, she immediately asks for help. And if I'm busy, she does keep trying and usually she figures it out. All right. Sometimes she doesn't. Sometimes she needs a little more help. And that's okay. If you try this and you struggle, but you try it and you still need a little more help, ask me. All right. Come to office hours, snap a picture, send me an email. Hey, am I on the right track? I will help you, but try it before you ask. Give yourself a shot before you ask. All right? Don't just hit a wall and go, oh my God, I can't do this. I have to go get help. Give yourself a chance to try it before immediately deciding that you need help. As usual, I'll give you the final answer. What you're looking for is all right, that's what you should get as your final answer. Okay? All right, try it. Struggle. It's worth it, I promise. Okay. We have one more section in this chapter. No math in it.